Let us talk about discrete valuation rings. So first we start with discrete valuation. So discrete valuation, this is an onto map from a field k without 0 to integers. So this map is such that valuation of f times g is valuation of f plus valuation of g. Valuation of f plus g is greater or equal to minimum of valuation of f, valuation of g, and this f is not equal to g. And if you want to extend it to 0, then we put valuation of 0 as infinite. So this is discrete valuation precisely because you have integers here. If you just have valuation, then you just have real numbers here. So we have this field k, and this field k contains the subring r. So this subring is defined as those elements of the field whose valuation is greater or equal to 0. And this subring r has a maximal ideal, and this maximal ideal is precisely those elements of our field whose discrete valuation is strictly greater than 0. So notice you have greater or equal to 0, you have greater than 0 here. So we call R as a discrete valuation ring of the valuation V. So in fact, this is a local ring which has a maximal ideal M. So you have a local ring and you have a maximal ideal M. So we can always talk about the residue field R modulo M. Another thing to notice is that R lies within the field K. So R has to be an integral domain because it lies within a field. And further we will show that not only it's a local ring with a maximal ideal, it is also a principal ideal domain, and therefore it is a Noetherian too and a unique factorization domain. So each ideal of this ring R will be of this form: some pi to the I, where pi lies in the ring R, and this power I is the minimum valuation of all elements in the ideal. So this will become more clear as we discuss some examples and go over more properties of the discrete valuation rings. So we are just saying that it is a local ring with a maximal ideal and it is a principal ideal domain. So that essentially means that everything has to be generated by a single element. So any ideal will be of this form pi to the I. So all ideals are generated by the single element pi, and the maximal ideal is just generated by pi. So dimension of R is 1, which essentially means that spec of R is precisely just 0 and this maximal ideal M. So it has just two elements in it. So we set this pi which generates the maximal element M as 1 and call this pi as uniformizing parameter. So this is very important. So furthermore, any f which you take in k and it is not 0, this has a unique factorization. You can write f as u times pi to the n, where u is a unit and this valuation of u is 0. So we have talked about a lot of things here which we will need to prove, but anytime you think of a discrete valuation ring, you need to know what the valuation is, what field it lies in, and what is the maximal ideal. And this is a very important concept, and as we go further along we will see its uses in algebraic geometry also. So let us stop here and go to some examples before we come back and prove things. So the first prototypical example is Laurent series. So this is how it is written. Elements are of this form. They are power series. They go all the way to infinity, and that's why you have these round brackets. So CI t to the I, where CI is in k, Cn is not 0, then valuation of f is n. So Cn is not 0 means n is the lowest element here. So valuation of f is n. And corresponding discrete valuation ring is this power series in T. So now p-adic valuation. So this is very important. So fix a prime in integers, and for any rational you can write it as p to the n a over b. So valuation of r is n. And the corresponding discrete valuation ring, we write it like z and this bracket p, which means localization of z at prime p. Basically it means that the denominator will not be divisible by p for the discrete valuation ring, precisely because of the fact that our valuation ring has to be greater or equal to 0, so you cannot have any prime in the denominator, and that is what is precisely localizing at a prime. So localizing at a prime would mean that all the elements which do not lie in the prime ideal. So again, notice here, again we want valuation to be positive, so that's why we have these square brackets here, so as to you start with a positive, there are no t to the negative powers here, precisely because we want the valuation to be greater or equal to 0. Otherwise this n could be negative. In the total ring it could be negative, but in our discrete valuation ring it has to be positive. So let us now prove these properties. So now we prove the discrete valuation ring is a Euclidean domain, and once you show it as an Euclidean domain, since Euclidean domains lie within principal ideal domains, that means that discrete valuation ring is a PID, and the principal ideal domains lie within unique factorization domains, so discrete valuation ring is a unique factorization domain, and unique factorization domains are integrally closed in their field of fractions, so therefore you can call, or you can say that discrete valuation rings are also integrally closed in their field of fractions. So now let us prove this. So you put norm of 0 as 0 because valuation of 0 is infinite, so here you put it 0, but otherwise if the element is not equal to 0, you put norm equals to valuation. So if norm of f is less than norm of g, you just put f is equal to 0 times g plus f. If norm of f is greater or equal to norm of g, so this norm of f is going to be valuation of f greater or equal to valuation of g, and you put it as valuation of f minus valuation of g is greater or equal to 0. That precisely means that you have some element q which is of the form f by g, so whose valuation is like this, and that's what you write as f is equal to q times g plus 0. So notice that remainder is 0, and that is precisely because we have valuation like this. So here you have f g inverse, so you have a minus sign here, so this we'll prove in a minute, but that is it. So you see the remainders are always 0, and since you have this division algorithm here working for you, it is a Euclidean domain and the rest follows. So now let us come down to the nitty-gritty of what we have said here and prove this. So first thing we want to show is that valuation of 1 is 0 and valuation of x inverse is minus this valuation of x. So before we show this, let us show an implication of this. So say x is the element of k, that is our this field k, and x does not lie in R. So x does not lie in R means that valuation of x has to be less than 0. It is not 0, it is less than 0 because x does not lie in R. So if it is less than 0, then minus valuation of x will be positive if this is, so minus valuation of x is positive, and minus valuation of x is valuation of this x inverse here, so that means valuation of x inverse is positive, and these are precisely the elements which lie in the maximal ideal here. So if x lies in K and x does not lie in R, this implies this x inverse lies in M, and this is just an implication of number 1 here. So let us now prove this number 1. So you notice that valuation of 1 is, because 1 is 1 times 1, and you use this thing, this is valuation of 1 plus valuation of 1, cancel this out, you get valuation of 1 as 0. Again you can write, so here we were writing 1 equals to 1 times 1, here we are writing 1 as x times x inverse. So again, using this property you write it like this, but we have just shown that valuation of 1 is 0, so valuation of x inverse is minus valuation of x, what we wanted to show. We now describe the behavior of units in a discrete valuation ring. So for every unit in this ring R, we will have the valuation of the unit is 0. So if you have a unit, its valuation is 0. In fact, if the valuation of something is 0, it is a unit in R. So obviously, if the valuation is 0, you have units, and all other elements which lie within M are non-units, and this will make it a maximal ideal. So this will follow from the fact that if A times B is 1, if so we are going in this direction first. A is a unit, so there exists some B in R, so that AB is 1. Now take valuation, use this formula, and then valuation of 1 is 0, you get 0. But we are saying that A and B both lie in R. A is a unit of R and B is inverse of A. They lie in R and their valuation has to be positive. So valuation of A and B has to be positive. So it has to be the case that valuation of A is 0, because you're adding two positive quantities and you are trying to make it 0. So therefore it will be 0. Now in the other direction, you start with valuation of A is 0 and you want to show that this is a unit. And this is precisely a unit because if valuation of A is 0, then valuation of A inverse, which is minus valuation of A, is also 0. Now if valuation is 0, by this criteria, valuation is greater or equal to 0. That means this A inverse lies in R. And therefore A is a unit because its inverse lies in R. So units are done. Now we talk about elements are of this form. So let valuation of f be n. Then valuation of f times pi to the minus n. We are saying valuation of pi is 1, which we have set as 1. So use this formula again. So you get valuation of f, and then you have, you can say, plus valuation of pi to the minus n, which will become n minus n, which will be 0. So valuation of this would be 0. So if this is 0, we know that an element is a unit if and only if its valuation is 0. So that means this is a unit. Say it is u. So you set this equals to u. So that means f is equal to u times pi to the n, and that is what we wanted to show. So finally we are trying to show that all the ideals are of this form. So any ideal we are saying is pi to the I, where this I is determined by the minimum valuation. So you take the valuation of all the elements, you keep getting integers. Every time you take a valuation you get an integer, and we are working in the ring R, so all these integers are positive numbers. So you take the minimum possible number, put it here, and that gives you the ideal. So let valuation of some y be n, and this n is minimal for y in the ideal I. So some ideal I. So then y differs from pi to the n by a unit, because valuation of y is n and we are saying that valuation of pi is fixed at 1. So both of them have the same valuation. So y you can write it as u times pi to the n, because they have the same valuation, and just by this logic here it could be 0, so that would make it a unit. So they differ by a unit. So that means because y lies in the ideal I, so this would imply y is u times pi to the n. This implies pi to the n lies within the ideal, and we will show it. Actually there is an equality here, because if you pick up any element in the ideal I, then valuation of a is greater or equal to n, because our ideal I is determined by this minimal valuation n. So the valuation is greater or equal to n. So the valuation of this a pi to the minus n is greater or equal to 0, because this you can write it as valuation of a, then minus n times valuation of pi. This is just 1, but this is greater or equal to n, so this is greater or equal to 0. So that means this element has to lie in the ring R, because this is the criteria is greater or equal to 0. So this lies in ring R. That means a actually lies within the ideal generated by pi to the n, and this is true for all elements. So therefore there is an equality here.